Okay, so basically this is then the number subtracting the floor is the fractional component. And there are other random variable that you may want to sample is can somebody raise other examples of random variables that may be appropriate for other scenarios?
Wait, other random variables like actual variables or distributions?
Either way.
I was gonna say like there's a lot of stuff that's like Poisson.
There is a lot of things that are Poisson, which is actually
which is a like Gaussian squared. Right.
Right. So Poisson process is actually a random process. So it's a very common random process where you have multiple events that can occur at uncertain times. And what's special about Poisson is that the occurring of the next event is memoryless, right? I mean, so basically knowing how long it has passed since the last event has happened does not give you any information on how long it'll take for the next event to happen. Right, it's like if you're waiting for buses to come, right? You come to a bus station, and if the arrival of buses is according to a Poisson process, then if you ask around and or see how many people are already standing there, gives you no information on how long you have to wait further. I mean, in practice, you can argue maybe some buses are more like that than others. But this is Poisson process. But what's interesting is that the interval between two events satisfies a distribution called the exponential distribution. So exponential distribution is what gives you the memoryless property. So basically, conditioned on the random variable is greater than any given quantity. Okay, the conditional distribution of the random variable is actually the same as the original random variable. So maybe I think it's easier to draw over here. So let's say I have the x and the PDF of x. All right. For exponential distribution, the PDF is an exponential function. And what's remarkable is that if I know the random variable is greater than a certain number, which is the case when you are conditioning that if you go to a bus station, the last bus has was here like x0 time ago, then the conditional expectation here, if you blow it up to here, is actually like a shifted version of the original random variable. So that's what's remarkable about exponential distribution. That's the memoryless feature. So if you want to model something, a random variable that has no memory, exponential distribution is a good one. So how do you sample from exponential distribution? Actually, not many computational tools doesn't give you a very a function to directly sample from that, but there is a very easy.
Radiation?
Huh?
By measuring radiation.
By measuring radiation. Yeah, that's right. That's right.
Suggested.
It's being suggested on Monday. Yes, that's actually the mean time between your Geiger counter actually counts is actually a very good exponential random variable. But MATLAB doesn't give you a radiation counter. So the best way to do that is actually to take a uniform random variable like the A we had before and transform it using what?
Lambda e to the minus lambda. The exponential.
Actually, the opposite of that. I want to take a log of A. So if I do a histogram of minus log A, this is what I get. Okay, so basically the logarithm maps a uniform distribution from 0 to 1 to an exponential distribution, but in the negative axis, right? Because
Because it's 0 to 1 instead of 1 to
yeah, instead of 1 to infinity, or if you take a log of 1 over a, it'll give you directly the exponential distribution. All right.
I guess that's also one of the really nice things about uniform distributions is you can always make other things from it.
Yeah. So if you know the CDF, if you know the cumulative density function of any random variable, there is a trick to randomly sample uniform distributions and map it to that particular random variable. So think of this. How to sample any distribution given its CDF. All right. So what is CDF? CDF is the cumulative distribution function. I have x and CDF of x. So CDF of x always starts from 0 when x is minus infinity, right? So CDF of x is defined as the probability that x, your random variable x, is less than that small, let's do this small x. So CDF is that. That is why when small x, this small x is at minus infinity, the probability that the random variable is less than minus infinity is of course 0, right? So it always starts at 0 and ends when small x is positive infinity at what?
1.
At 1, right? Because the probability that my random variable is less than infinity is of course 1. So any CDF is going to be something like that, where this is 1. All right, that's nice because between 0 and 1 is actually exactly the range of a uniform distribution. So a very reasonable hypothesis is that if I randomly sample in the y-axis between 0 and 1 and use the inverse of the CDF to map each sample into the x-axis, what do I get? Do I actually get a random variable that satisfies the original distribution? Yes, I do, right? And you can formally prove that by saying that if I sample uniformly, let's say sample my y uniformly, then the probability that my big Y, my uniform random variable less than small y is actually equal to what? Is equal to y, because big Y is uniform 0 and 1, right? Okay, and if I then also, because the CDF is monotonically increasing according to the definition, right? If I increase my x, my CDF of course has to increase because the probability of that bigger x is including the probability of that small x. So the probability y less than small y is actually equal to the probability that x is less than small x, which is actually the CDF of x. So basically by doing that, you can guarantee that you are sampling the original distribution, right? Or in other words, if you have a uniformly dense sample from here, when you map it back to the x-axis, you can think of the PDF, right, being then the PDF of that x is actually the PDF of y, which is equal to 1 always, divided divided by the slope of the CDF, right, divided or multiplied. Right, the width is divided by the slope of the CDF, which is the PDF. And since the width is divided, the density is going to be multiplied, right? Because the density is the mass probability per width. So for this particular delta y, you get a delta x, that is delta y divided by the PDF of x, right? So the rho of x is equal to rho of y, which is equal to 1 times PDF of x. So the density you get is what you want. All right. So this basically gives you a tool to sample any PDF, and if you follow this for the exponential distribution, you get exactly the logarithmic transformation we are using before, right? The logarithmic transformation is basically the inverse function of the cumulative density function of the exponential distribution, right?